October 15, 1891, in Manchester, New Hampshire. Without warning, a 56-ton flywheel ripped itself apart, hurling iron through brick and killing 3 workers in seconds. This was not a fire, and it was not a boiler explosion. It was stored rotational energy, released at once. It was one of many disasters that made the spinning giants both vital and deadly. But why did factories trust such immense power, and what finally stopped the carnage? Steam engines in the late 19th century were the beating heart of American factories, but their power came with a catch. Each piston stroke delivered a jolt of energy, and then fell silent until the next. This pulsing rhythm was at odds with the demands of textile mills, where thousands of threads and looms required steady, unwavering motion. Any hiccup, no matter how brief, could snap threads, jam machinery, or ruin entire batches of fabric. In a world where downtime meant lost wages and missed orders, even a few minutes of idle machines carried a heavy price. To bridge that gap, engineers turned to the flywheel, a massive spinning disc often weighing between 20 and 50 tons. Its job was simple, but vital. Absorb the surges of power from the engine and smooth them out, releasing energy between strokes to keep the line shafts turning at a constant speed. In the largest mills, a single steam engine drove a main shaft running the length of the building, with belts and pulleys distributing motion to every floor. The flywheel became the stabilizer at the system's core, preventing stalls and keeping production on track. Restarting a steam engine was no small task. It meant shutting down boilers, waiting for pressure to drop, and then slowly building it back up, a process that could take hours and burn through fuel and labor. Larger flywheels let factories ride out sudden changes in load, such as many looms engaging at once, without risking a costly shutdown. The logic was clear. Concentrate energy in one place to protect the flow of work. The risk was enormous, stored power spinning in the middle of the factory, and it was a price many owners and engineers were willing to pay. A flywheel in a late 19th century mill was an object of staggering proportions. Typical examples weighed anywhere from 20 to 50 tons, with the largest sometimes tipping the scales at 100 tons or more. Diameters stretched across 30 feet, and in the most ambitious factories, some wheels spanned over 40 feet, so large they filled entire engine rooms, their curved rims brushing close to walkways and workspaces. Despite their immense size, these machines spun with a deceptive calm, turning at just 30 to 60 revolutions per minute. To the eye, the motion seemed gentle, almost slow, but at the rim, the story changed. On a 30-foot wheel running at 60 revolutions per minute, the edge moved at nearly 95 miles per hour, faster than a speeding car, just inches from brick walls and iron columns. The invisible threat lay in how energy was stored. Rotational energy increases with the square of speed, so even a modest rise in revolutions per minute could send the forces in the rim soaring. A 10% increase in speed, for example, meant more than 20% more stress pressing outward, locked in the iron. The energy did not fade when the machinery slowed or the load dropped. It stayed trapped in the spinning mass, waiting for friction to bleed it away. For workers, the flywheel became part of the scenery. No steam, no fire, no warning signs, just the steady whir of metal. Its presence was both ordinary and immense, a physical heart at the center of the building, holding more power than most could imagine, all contained in a single, silent rotation. Cast iron was the material of choice for these enormous flywheels, favored for its low cost and ability to be poured in massive sections. But cast iron has a hidden weakness. It excels at handling compression, yet its tensile strength, the ability to resist being pulled apart, is far lower. In a spinning flywheel, it is the rim that suffers the most, stretched outward by centrifugal force with every turn. The larger the diameter, the greater the force. Many wheels were too large to cast in one piece, so they were built from multiple segments bolted together. Each joint became a point where stress could concentrate, and even a tiny flaw, a bubble, a crack, a casting gap could grow dangerous over years of use. The physics are unforgiving. As speed increases, the force pulling the rim apart rises with the square of the revolutions per minute. A 10% overspeed, caused by a sticky governor or a sudden drop in load, does not just make the wheel spin a bit faster. It can push the internal stress more than 20% higher. That is enough to take a rim already close to its limit and drive it past the breaking point in a moment. Once a crack forms, it can race through the brittle iron faster than anyone can react. Fatigue from daily cycles, machines engaging and disengaging, belts slipping and grabbing, adds to the risk. In the era before X-ray inspection, these cracks were invisible, hidden deep inside the metal. The first sign of trouble was often the last, a sudden, explosive break that turned stored energy into flying debris. Engineering journals from the 1890s read like a litany of disaster, recording flywheel bursts in mills, steelworks, and power stations across North America and Europe. Reports describe similar scenes: a sudden, deafening crack, fragments of iron slicing through brick and timber, work halted as debris rained down. In Providence, Rhode Island, a factory flywheel burst with such force that metal pieces were found across a canal far beyond the mill's walls. At Amoskeag, a 64-ton rim fragment launched 200 feet through the air, collapsing floors and shattering windows. These were not isolated tragedies. Each incident echoed the same pattern of risk, repeated in different towns and factories, but always with the same violence. Despite the frequency, records remained scattered and incomplete. There was no central authority tracking these failures. Most incidents only reached public attention if they killed workers or destroyed buildings. Smaller bursts, near misses, and close calls slipped through the cracks, lost to local rumor, or buried in trade publications. The true scale of the hazard is hidden in these gaps, a pattern visible only in hindsight and pieced together from fragments of newsprint and engineering notes. When disaster struck, the response was forensic but narrow. Investigators weighed shattered iron, mapped the arc of debris, and measured the thickness of breached walls. Reports tallied costs and casualties, but rarely questioned the system itself. Failures were chalked up to a bad casting, a worn bolt, or a momentary overspeed, never the underlying design that put so much energy at the heart of everyday work. The cycle of repair and rebuild continued, with little appetite for deeper change, even as towns reeled from the aftermath and families mourned the dead. Containment became the first answer to the flywheel problem. Some mills built thick timber or steel housings around their wheels, hoping to stop fragments if a rim burst. Others turned to pits, sinking the flywheel below floor level in a brick-lined well. In theory, a deep enough pit could trap most debris and keep it from slicing through crowded workspaces. But heavy iron moving at highway speeds often found weak points, breaking through brick, splintering beams, or launching upward into floors above. This was a sudden, violent danger that barriers sometimes could not fully control. Adding these barriers ate up valuable space and made maintenance harder. To lower the risk further, managers imposed speed limits and reduced engine loads, cutting the stress on rims. Maintenance became more difficult and operations were more constrained. This approach worked to reduce failures, but it came at a cost. Less power meant slower production, and every safety upgrade was weighed against lost output. The logic was always a compromise: protect workers as much as possible while keeping the mill running. Steel began to replace cast iron in critical flywheel rims, offering a crucial advantage. When pushed past its limits, Steel could bend and deform, releasing energy gradually rather than shattering. Electrification brought the real transformation. Instead of one massive engine driving the entire mill, factories installed banks of smaller electric motors, each powering just a few machines. A failure no longer meant a shutdown across the entire building or deadly debris. It meant just one stopped motor. Downtime plummeted, insurance premiums dropped, and the risk of catastrophic failure faded into memory. As electric systems became more reliable and affordable, market competition forced even the most traditional mills to adapt. The economics of safety and productivity combined, making the old spinning giants not just dangerous, but obsolete. Stored energy, whether in steel, batteries, or data, still demands respect. Modern systems fail too. Only when we design for the worst can we limit disaster. The lesson holds. Invisible risks shape our world long after the wheels stop spinning. What overlooked dangers do we accept today?